Dear students, let us start new chapter of coordination chemistry and its title is SIDGWICK theory. Scientist SIDGWICK put forth the new theory which is put forth by SIDGWICK. It is known as SIDGWICK model, in which we are going to discuss EAN rule. This model was based on the 2 points which are very important. So let us see the first point. Werner's primary valency is the positive valency, which is also called as electrovalency. What is electrovalency? When metal atom loses electron, at that time there is formation of electrovalency. So this is the first point on which SIDGWICK model is based. Second one, Werner's secondary valency is the electron pair sharing or coordinate valency. We know that in formation of coordination compound metal complex, what happened? Ligand acts as donors and metal ion acts as acceptor of electron pair, and there is formation of dative bond or coordinate bond between metal and ligand. We know that this bond is shown by electron pairs are donated from ligand to metal. See here, this is the example. Nickel is coordinated with ammonia molecules. From ammonia molecules, nitrogen donates electron pair to nickel ion, and hence ammonia molecule is acts as donor molecule while nickel ion is acts as acceptor ion, and in this way there is formation of dative bond, coordinate bond between ammonia and nickel, that is the ligand and metal ion. So this is shown with the help of this figure. So in figure there are 6 coordinate bond between ligand and metal ion, that is ammonia and nickel ion. Ammonia molecules donate electron pair to nickel ion, which is shown by arrow. The number of bonds formed is equal to coordination number of metal ion. Here the coordination number of nickel is 6, and therefore there is formation of 6 bonds between nickel and ligand, that is ammonia molecules. Let us turn to next concept, which is called as effective atomic number, or in short it is also called as EAN. SIDGWICK introduced this concept to clear the tendency of metal ions to form stable complexes. So when a ligand attaches to metal ion, according to SIDGWICK, there is formation of stable complexes. But when these stable complexes are formed, according to SIDGWICK series, metal ions accept electron pair from ligands till they achieve inert gas configuration or effective atomic number of next inert gas. And hence SIDGWICK, according to SIDGWICK, as metal ion achieves inert gas configuration or atomic number of next inert gas, and due to this the metal complex becomes stable. So the metal ions achieves stable inert gas configuration by accepting electrons from donor atoms or ligand, and the stability of complex is due to the inert gas configuration. Now see definition of EAN, which is also called as effective atomic number. What is this? The sum of electrons donated by ligand and number of electrons of metal ion or atom while forming complex is called EAN. It is also the number of electrons associated with the central metal ion in the complex is called as EAN. Agreed? Now how it is calculated? EAN is calculated by subtracting the number of electrons lost in ion formation from the atomic number of the metal and adding number of electrons accepted from the ligands. In complex formation, what happened? Ligand donates electron to metal ion. Okay, and during formation of complex, what happened? Metal undergoes formation of metal ion. At that time, there is loss of electrons. So we have to subtract this number of electrons, okay, from atomic number of the metal, and we have to add the number of electrons which are donated by ligand. For this, SIDGWICK put forth the formula EAN is equal to Z minus N plus X, which is very important formula. With the help of this formula, we are going to calculate the effective atomic number of the metal. See here, Z is the atomic number of metal atom. N is the number of electrons lost in ion formation, and X is the number of electrons accepted by metal, or it is also calculated by multiplying coordination number with 2, because if coordination number is 4, each ligand donates electron pair, that means 2 electrons are donated to metal ion, therefore 4 into 2, 8 electrons are donated to central metal ions. That means these 8 electrons are accepted by metal, therefore this is about X. So remember well, EAN is equal to Z minus N plus X. Let us explain this effect atomic number concept with the help of example. Example number 1. This is a hexamine cobalt ion. On this ion there is 3 plus charge. So we know that the atomic number of cobalt is 27. That means number of electrons in cobalt atomic number is 27. Therefore 27. This is the value of Z. Next, number of electrons lost in CO3 plus formation. See here, in this complex, ammonia molecules are ligand. Therefore, this 3 plus charge is from cobalt, and therefore, to form this CO3 plus ion, cobalt must have to lose 3 electrons. Therefore, N is equal to 3. As here there are 6 ammonia molecules attached to cobalt, therefore 6 ammonia molecules donates 6 into 2, that means 12 electrons which are accepted by metal ion. Hence, substitute these 3 values in our formula. EAN is equal to Z minus N plus X. Therefore, 27 is the Z, minus 3 the electrons lost for formation of CO3 plus, and plus 12 electrons which are donated by ammonia. So this becomes 24 plus 12, that means 36. We know that this is the atomic number of krypton. Okay, krypton is the inert gas, and therefore we say that this complex obeys effective atomic number rule, that means EAN rule. Got it? Then see example number 2, K4FeCN6. Here first calculate how Fe loses the electron. See, 6 cyanide ions are attached to Fe, and here there are K4, that means plus 4 charge. That means on square bracket there must be minus 4. So how this minus 4 is obtained? Cyanide 6, that means minus 6, and Ap, there must be 2 plus charge on this ion. Got it? So Ap carries plus 2 charge. Now start. Number of electrons in Ap, that means atomic number of Ap is 26. The value of Z is 26. Just we have discussed, there is formation of Ap2 plus ion. To form Ap2 plus ion, Ap must lose 2 electrons, and therefore the value of N is equal to 2. As there are 6 cyanide ligands, this ligand donates 6 into 2, 12 electrons, which are accepted by iron metal ion. Substitute these values in this formula. EAN is equal to 26 minus 2 plus 12, Z minus N plus X. This also becomes again 36, which is the atomic number of inert gas, that is krypton, and hence this complex obeys effective atomic number rule, EAN rule. Next complex, CuCN4 3 minus. Here see on square bracket there is 3 minus charge. There are 4 cyanide ions, that means minus 4. So for this 3 minus, copper must carries plus 1 charge. Now say atomic number of copper is 29, and therefore the value of Z is 29. For formation of Cu plus 1, copper must lose 1 electron, therefore N is equal to 1. Now there are 4 cyanide ligands which donates 4 into 2, 8 electrons, which are accepted by copper, that means metal ion. Substitute these values in this formula. EAN is equal to Z minus N plus X, that means 28 plus 8 is equal to 36, which is again the atomic number of krypton. Hence this complex ion also obeys EAN rule. Next example, PtCl6 2 minus ion. Again see how this 2 minus ion is obtained. 2 minus charge is obtained. So chloride 6, therefore minus 6. For this 2 minus, on platinum there must be plus 4 charge. Therefore plus 4 minus 6, it becomes minus 2. Start. Electrons in platinum, atomic number is Z 78. Therefore Z value is 78. Number of electrons lost to form Pt4 plus ion, that means N is equal to 4. 4 electrons are lost. Then there are 6 chloride ions which donates 6 into 2, 12 electrons, which are accepted by metal ion. Substitute these 3 values in this formula again. EAN is equal to 78 minus 4 plus 12, it becomes 86, which is nothing but the atomic number of radon, and this complex obeys EAN rule. Again, next example, PdNH3 4 plus ion. Ammonia molecules are neutral, hence the 4 plus charge is from palladium. Start. Electrons in palladium, that means atomic number of palladium is 46, therefore value of Z is 46. Just we have discussed, Pd4 plus ion is formed, that means there is loss of 4 electrons, so N is equal to 4. There are 6 ammonia molecules, so 6 ammonia molecule donates 6 into 2, 12 electrons, which are accepted by palladium. Substitute these values in this formula. EAN is equal to 46 minus 4 plus 12, it becomes 42 plus 12, it becomes 54, which is the atomic number of xenon. Hence we say that this complex obeys EAN rule. Xenon is also inert gas atom. Next example, nickel tetracarbonyl molecule. So here on this square bracket there is no charge, so number of electrons in nickel atomic number is 28, so Z value of Z is 28. No electrons are lost for formation of Ni on which there is zero charge, therefore N is equal to 0. 4 carbonyl molecules, so therefore 4 into 2 it becomes 8, so 8 electrons are accepted by metal ion, hence EAN is equal to 28 minus 0 plus 8, it becomes 28 plus 8, 36. Again this is the atomic number of krypton, which is nothing but the inert gas configuration, and hence this complex obeys EAN rule. So these are the obeying complex of EAN rule. Now let us see some examples of disobeying EAN rule. Complexes disobeying EAN rule. First one, K3FeCN6. Here again 6 cyanide ions are attached to Fe. Here there is potassium which is present outside the square bracket plus 3. This plus 3 is neutralized when there is minus 3 charge on the square bracket. So how this minus 3 charge is obtained? 6 cyanide, therefore minus 6. On Fe there must be plus 3 charge. Got it? On Fe there must be plus 3 charge. So Z of Fe is 26. So value of Z is 26. Just we have discussed there is formation of Fe3 plus ion. That means value of N is equal to 3. There are 6 cyanide ions which donates 12 electrons which are accepted by iron metal ion. Substitute in this formula EAN is equal to 26 minus 3 plus 12. Now it becomes 35. This is nothing but nothing. It is not agreed with atomic number of any inert gas. Therefore, we say that this complex is disobeying EAN rule. Okay. Second, NiNH3 2 plus ion. Here 6 ammonia molecules. These are neutral. Therefore, 2 plus charge is from nickel. Okay. So nickel is present in Ni2 plus ionic form. Z we know that the atomic number of nickel is 28. There is formation of Ni2 plus ion. That means the value of N is equal to 2. 2 electrons are lost. There are 6 ammonia molecules which donate 12 electrons to nickel which are accepted by nickel ion. Substitute this value in this formula. So 28 minus 2 plus 12 it becomes 38. So this is not agreed with any atomic number of inert gas, and therefore this complex is disobeying EAN rule. Next one, NiNH3 2 plus ion. Number of electrons in nickel Z value is 28. Here again there is formation of Ni2 plus ion. So value of N is equal to 2. 6 ammonia molecule donates 12 electrons which are accepted by metal ion. So again EAN, this total becomes 38. Hence we say that this is again disobeying EAN rule. Then the next one, here chromium attaches to 6 ammonia molecules. There is 3 plus charge, and this 3 plus is from chromium because there is no charge on ammonia. The atomic number of chromium is 24, so value of Z is equal to 24. Cr3 plus ion is formed, therefore value of N is equal to 3. 6 ammonia molecules donate 12 electrons and which are accepted by chromium. So EAN is equal to 24 minus 3 plus 12, it is 33. Okay, and it is not the atomic number of any inert gas. So we say that this complex is disobeying EAN rule. Then see next point, merits of EAN effective atomic number. With the help of this concept, it is easy to predict the coordination number of central metal atom or ion. If 8 electrons are donated to central metal ion, we say that the coordination number of metal ion is 4. If 12 electrons are donated to central metal ion, we say that 12 electrons are donated to central metal ion. Second merit, this concept explains the stability of many complexes. The complexes obeying EAN rule are considered as stable complexes. So, SIDGWICK, according to SIDGWICK, the complexes which obeys EAN rule, they are more and more stable. Now see limitations of SIDGWICK model. Some scientists, this model is not uniformly applied to all complexes. There are many complexes which are stable even though they do not obey the EAN rule. We have discussed some examples disobeying. In that we have discussed one of the complex of iron. Actually that complex is stable though it is not obeying EAN rule. This is the limitation of SIDGWICK model. Second limitation, now see, we know that in the formation of metal complex, ligand donate electrons and metal ion accept these electrons. Okay, due to this what happen, there is formation of negative charge on metal ion and which decreases the stability of complex. Ligand donates electrons to metal ion, that means negative charge is donated, that means negative charge is increases. Then how we say that the metal complex become stable? It is not increases, it is decreases. Then see next limitation. We know that in case of ammonia molecule, nitrogen is the electron pair donor atom, while in case of H2O on oxygen there is lone pair of electron. But according to scientists, the 2s2 electron pair in NH3 and H2O is non-bonding. If the electron pair is non-bonding, how we say that there is formation of a dative bond, coordinate bond between metal ion and ligand. This is one of the limitation. The next one, the ionic bond is present in fluoro or chloro complexes between central metal ion and ligands. It is not covalent. In coordination chemistry, we say that fluoride ion and chloride ion, they donate electron pair to central metal ion and there is formation of coordinate covalent bond. But we know that when chloride ion and fluoride ion are attached to metal ion, what happens? There is electrostatic force of attraction between metal ion and these ligands. That means that bond is ionic bond. It is not dative bond. This is one of the limitation of SIDGWICK theory. Then very important limitation, this EAN concept do not explain geometries of complexes. We have discussed there are many types of complexes in which the coordination number is 4. When the metal ion shows 4 coordination number, it shows square planar geometry or tetrahedral geometry, but it is not explained with the help of SIDGWICK model. These are the limitations of SIDGWICK theory. So friends, we stop here. We have finished this chapter, SIDGWICK theory. In next lecture, we discuss the valence bond theory, Pauling's valence bond theory. Thank you.